All right, welcome back to section 6.5. This video will cover examples 8, 9, 10 in your notes. You'll learn how to use de Moivre's theorem to find the powers of complex numbers and how to find the nth root of complex numbers. So say you've got a complex number written in trig form, namely z is equal to r times the quantity of cosine theta plus I sine theta. So this trig form is used to raise a complex number to a power. So to accomplish this, what we'll do is actually apply the multiplication rule. So if we have z, again, as r cosine theta plus I sine theta, and we were to multiply z times z, or come up with z squared, we would multiply our moduli, so r times r would be r squared, open parentheses, we have cosine, we add our arguments, so theta plus 2 theta, plus I sine of theta plus theta again would be 2 theta, close brackets. Let's do it again. So z cubed is the same thing as z times z squared, or z cubed is equal to r times r squared would be r cubed, open brackets, theta plus 2 theta would be cosine of 3 theta, plus I sine of 3 theta. Let's do it one more time. So if we're looking for r to the 4th, we could have z times z cubed, or let's see, r times r cubed is r to the 4th, open bracket, cosine, add your arguments, theta plus 3 theta is 4 theta, plus I sine of 4 theta. So generalizing this a little bit, so I see if I were to raise z to the n power, I would have r to the n power, open bracket, cosine of n times theta, plus I sine of n times theta. So we have arrived at de Moivre's rule. So again, de Moivre's rule says if you've got a number in trig form and you raise both sides to the n power, then the result, or z to the n, is equal to r to the n plus cosine of n theta plus I sine of n theta. All right, in example 8, we're asked to use de Moivre's theorem to find the quantity of 1 plus root 3i all raised to the 12th power. But with de Moivre's theorem, we need first a number in trig form before we can apply our formula. The only thing that is given to us at this point is that n is equal to 12. Know that because it's the exponent. So right now, looking on the inside of these parentheses, 1 plus root 3 is in standard form, a plus bi, not in trig form. So task number 1 is to convert 1 plus root 3i into trig form. And remember, that's r, open parentheses, cosine of theta plus I sine theta. Well, let's draw a quick sketch of 1 plus root 3 on the complex number plane. So my a value is 1, and my b value is root 3. So over 1 of root 3, here's theta. So my r value is equal to the square root of a squared plus b squared. So underneath it looks like 1 plus 3, or the square root of 4. So my r value comes out to 2. The next thing we need is this value of theta. Well, we can use the fact that tangent of theta equals opposite over adjacent. Take the inverse tan to get theta. Or simply by looking at our diagram, I see theta is in the first quadrant. So what value of theta has a tangent of positive root 3? From our unit circle, we know that theta must be pi over 3. So now we're able to convert 1 plus root 3i into trig form. So my z value, so z is equal to r, which is 2, open parentheses, cosine pi over 3 plus I sine pi over 3. So we now need to raise everything to the 12th power. So we're going to raise this to the 12th power and everything over here to the 12th power. So we have z to the 12th is equal to 2 to the 12th times, open bracket, cosine. So now we need n times theta. Remember, n was 12. So 12 times pi over 3 plus I sine. N times theta again is 12 times pi over 3. It's helpful to notice that both arguments for the cosine and the I sine are the same number. So simplifying this, we get 2 to the 12th is 4,096. Open bracket, cosine. Let's see, simplify this into 4 pi plus I sine of 4 pi. So I know cosine of 4 pi is coterminal with 2 pi and coterminal with 0 pi. So I'm going to simplify this as 4096 times cosine of 0 plus I sine of 0. Well, I know the cosine of 0 is 1, and the sine of 0 is 0. So when I distribute this 4,096 through, I get 4,096 times 1 plus 0, or simply 4,096. So let's do a quick recap on this problem. So in order to apply de Moivre's rule, the first thing we needed to do was get 1 plus root 3i into trig form. Remember, trig form was r times open parentheses cosine theta plus I sine theta. We drew a quick sketch of 1 plus root 3 and found our r was 2 and our theta was pi over 3. So once we had 1 plus root 3i into trig form, we raised both sides to the 12th power. So using the formula, 2 times 12 became 4,096, which carried straight down. Inside, cosine of n theta became cosine of 12 times pi over 3. And we had the same argument for I sine of 12 times pi over 3. We simplified cosine of 4 pi into cosine of 0 because it's coterminal. And again, our arguments are the same. We cleaned up inside, distributed the 4,096, and came up with z to the 12th as 4,096. All right, go ahead and try exercise 107 in your notes now. Again, draw a quick sketch of what does this complex number look like on the plane. You should be in quadrant 1. You also want to recognize that your n value is 3. Check your answer in the back of the book. Come back when you're done. So remember back into chapter 2 that we said that any degree of polynomial n has to have exactly n solutions. So if we have an equation such as x to the 6th minus 1, it's a 6-degree polynomial, meaning if you add all the real solutions plus all the imaginary solutions, you have to come up with 6 solutions. So if we tried factoring this to apply the zero product property, we'd have x cubed minus 1 times x cubed plus 1 is equal to 0. I see this first factor is actually a difference of cubes, which factors into x minus 1 all over x squared plus x plus 1. While the second factor is a sum of cubes, which factors in x plus 1 times x squared minus x plus 1. Everything's still set equal to 0. Well, this first factor, if we set equal to 0, we get x equals 1. So 1 down, 5 to go. And this third factor, if we set equal to 0, we get x equals negative 1. Try as we might, we cannot factor this second term. So if we apply the quadratic formula, we get x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So x equals negative 1 plus or minus, it's like square root of negative 3 all over 2. So x comes out to negative 1 plus or minus root 3i all over 2. Which remember actually accounts for two different solutions. The first one being x equals negative 1 plus root 3i all over 2. And the second being negative 1 minus root 3i all over 2. Similarly, if we apply the quadratic formula on this last factor, we get x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. See, we come up with 1 plus or minus, see, 1 minus 4 is negative 3 all over 2. So x equals 1 plus or minus root 3i all over 2, which again, we get two solutions. The top one being 1 plus root 3i all over 2. And the bottom counts like a jelly bean, x equals 1 minus root 3i all over 2. So if we take our real solutions, 1 and negative 1, and our four imaginary solutions, 2 from the first factor, 2 from the second, we've accounted for all 6 solutions, which is great because it was a 6-degree polynomial. With that in mind, I present to you finding the nth root of a complex number. So if you've got a number written already in trig form, it has exactly n distinct roots. And instead of doing all the work that we just did with a polynomial, we can actually apply this formula. So the nth root of r is equal to cosine of theta plus 2 pi k all over n plus I sine of theta plus 2 pi k all over n, where k starts at 0 and ends at n minus 1. So for example, if your nth root is 6, k values would be 0, 1, 2, 3, 4, 5, but not 6 because it's n minus 1. In example 9, we're asked to find the 6th root of 1. So the first thing that catches my eye on this problem is the fact that it's 6th root. So I know my n value is going to be 6. But looking at the definition from the previous slide, I see that we need to have a number that's already in trig form. And this 1 is not in trig form at all. It's in standard form, kind of, standard form being a plus bi. But a quick sketch of 1, well, that would just be on the real number axis. So here is 1 plus 0i. So in order to get it into trig form, we first need to know our r value. Well, our r value is just 1. And we also need to know theta. Well, it's on the real number axis, so theta must be 0. So in order to apply this formula, we need to apply it a total of 6 times for k equals 0, 1, 2, all the way up to n minus 1. But remember, n is equal to 6. So our k values would have to be k is equal to 0, 1, 2, 3, 4, 5, but not 6. So let's get some numbers in here just for reference. We said our r value is 1 and our theta is 0. All right, so make sure you're keeping your work organized. This will take some room on your paper. So first off, k equals 0. So out front, we've got the nth root of r. So n is 6, r is 1, open bracket, got cosine of theta, which is 0, plus 2 pi. My k value in this case is 0, all over n is 6, plus I sine of 0 plus 2 pi times 0 all over 6, close bracket. So let's start just by cleaning up this numerator. I recognize everything in the numerator becomes 0. 0 divided by 6 is 0. So I've got cosine of 0 plus I sine of 0. Now the 6th root of 1 is simply 1. So inside my brackets, cosine of 0 is 1 plus I sine of 0. Well, sine of 0 is 0. So this second term, my I term, cancels off. So the first root of 1 is simply 1. Box that answer. 1 down, 5 to go. All right, so same process for k equals 1. So out front, we still have the nth root of r, so the 6th root of 1, open bracket, cosine. My theta value is still 0, plus 2 pi. My k value is now 1, all over, my n is still 6, plus I sine of 0 plus 2 pi times 1, all over 6, close bracket. So again, let's clean up the numerator. I've got 2 pi all over 6, or cosine of pi over 3 plus I sine pi over 3. And the 6th root of 1 is still 1. Quick note, this number out front will stay the same for each of our calculations. So we've got 1 times, let's see, cosine of pi over 3 is 1/2, plus, let's see, sine of pi over 3 is root 3 on 2, I. So if we were to distribute the 1, the second root of 1 would be 1/2, plus root 3 over 2I. 2 down, 4 to go. All right, so for k equals 2, we still need the 6th root of 1 out front, so that number is going to stay constant. Open bracket, cosine of theta is still 0, plus 2 pi, k is now 2, all over 6, plus I sine, same argument. So I'm just going to simplify that to 4 pi over 6, close bracket. Well, let's see, out front, the 6th root of 1, we've just determined it's just 1. Cleaning up the numerator, there's my 4 pi over 6, or I've got cosine of 2 pi over 3 plus I sine of 2 pi over 3. So the 1 stays out front. Cosine of 2 pi over 3 is negative 1/2. Sine of 2 pi over 3 is positive root 3 over 2I. Distribute that 1. Our third root of 1 is negative 1/2 plus root 3 on 2I. All right, 3 down, 3 to go. All right, so remember R is still 1, N is 6, and theta is still 0. So K equals 3, the 6th root of 1 is still out front. Open brackets, cosine. Theta is still 0, plus 2 pi. K is now 3, all over 6, plus I sine of, let's see, my numerator looks like 6 pi. My denominator is 6. So I'm just going to write pi over here and save myself a little bit of work. So 1, open bracket, cosine of pi plus I sine of pi. So cosine of pi is -1. And sine of pi is 0. So I'm going to say plus 0i. Distribute that 1, and we get -1 plus 0i, or simply -1. All right, 4 down, 2 to go. So now on to k equals 4. So we still have the sixth root of 1 out front, times cosine, open parentheses, theta is 0 plus 2 pi, k is now 4, all over 6, plus I sine. Let's clean up this numerator. Here's 8 pi over 6. Well, 8 pi over 6 is 4 pi over 3. So we've got the sixth root of 1, simplifies to 1, times cosine of 4 pi over 3, plus I sine 4 pi over 3. Well, cosine of 4 pi on 3 is -1/2. Sine of 4 pi on 3 is -√3 on 2. Don't drop your I. That 1 is still hanging out front. So the fifth root of 1 looks like -1/2 minus √3 on 2i. And lastly, for k equals 6, remember r is still 1, theta is still 0, and is still 6. Now my k is 6. So out front, we still have the sixth root of 1, open bracket, cosine. Cosine of theta is still 0, plus 2 pi, k is now 5, all over 6, plus I sine. Let's see, my numerator is going to be 10 pi over 6, or 5 pi over 3. So the sixth root of 1 is still 1. Cosine of 5 pi over 3, plus I sine 5 pi over 3. See, cosine of 5 pi over 3 is 1/2. Sine of 5 pi over 3 is -√3 on 2, so minus √3 on 2i. That 1 is still hanging out. So the sixth root of 1 is 1/2 minus √3 on 2i. So all six roots of 1 would be 1/2 minus √3 on 2i. -1/2 minus √3 on 2i. -1, so that was 3. -1/2 plus √3 on 2i. 1/2 plus √3 on 2i. And +1. So there's a lot of plugging and chugging to go on these problems. If you give yourself enough room and time, the calculations aren't too challenging. They just take a little bit of time. All right, go ahead and try exercise 147 in your notes now. Make sure that you first get 1 into trig form. Make sure you recognize your r value, your theta value, and your n is 5. So when you count up, you're going to go from 0, 1, 2, 3, 4, but not 5. Check your answer in the back of the book. Come back when you're done. All right, in example 10, we're asked to find the 3 cube roots of z equals -2 plus 2i. So before we begin, let's start by just drawing a very quick sketch of this complex number. So we're going -2 on the real coordinate axis, and then 2 up. We've got z up here. So I see I'm in quadrant 2. So my r value is equal to the square root of -2 squared plus 2 squared. So r equals the square root of 8. Let's give that a quick highlight. My n value, because I'm finding the cube roots, is 3. And lastly, I need to find my value of theta. we know that tangent of theta is equal to b over a, where my b value is 2, my a value is -1. So tangent of theta equals 2 over -2. So for what value of theta does tangent come out to -1, knowing that you're in the second quadrant? So theta must be 3 pi over 4, or theta is 135 degrees. So before we begin plugging in numbers, let's get this z into trig form. So we've got z is equal to r, which we said was the cube root of 8, or 2 root 2, times cosine of 135 degrees plus I sine 135 degrees. So we're asked to find the 3 cube roots. So our k values are going to be 0, 1, and 2. So let's start with k equals 0, substitute in values. So we've got the cube root of 8, which is 2, big open brackets, times cosine of theta, which we said was 135. I'm working with degrees because as I work through this problem, I come into values that are not on the unit circle. For example, 165 degrees and 185 degrees, values that aren't easy to substitute out. So we will use our calculator in degree mode here shortly. So we've got cosine of 135 plus 2 pi 0 all over 3. Well, cleaning up the numerator, I see I've just got 135 all over 3, so plus I sine of 45. Let's see on the outside, cube root of 8 is 2, times the cosine of 45 plus I sine of 45. I'm going to swap these values out using the unit circle. We've got 2 over 1, cosine of 45 is root 2 on 2, plus I root 2 on 2, I. So this 2 in the numerator cancels with this 2 in the denominator, and with the second 2 in the denominator. So my first cube root of this trig number is square root of 2 plus root 2i. 1 down, 2 to go. All right, now I've got k equals 1. So we still have the cube root of 8 out front, which simplifies to 2 for each of these problems. Big open brackets. We've got cosine 135. I'm going to use 360 because we're working in degrees, times 1 all over 3. Plus, let's see, this numerator cleans up to 495 divided by 3 comes out to 165 degrees. So cube root of 8 is 2. Cosine of 165 plus I sine of 165. Close brackets. So grab your calculator and distribute this 2 to cosine of 165 and to sine of 165. So this first distribution comes out to -1.932 plus 0.518i. So we're rounded 3 decimals. And finally, for k equals 2, we still have the cube root of 8 out front, which of course is 2. Big open brackets, got cosine of 135 plus 360 times 2 all over 3. See, cleaning up the numerator, I've got 135, 360 times 2 is 720. Divide that by 3, and I get 285 degrees. Close bracket. So we've got 2 times the quantity of cosine of 285 degrees plus I sine of 285 degrees. So distribute that 2 to the first and second values. And I come up with 0.518 minus 1.932i. Box your final answer. All right, go ahead and try exercise 51 in your notes. Before we begin though, let's draw a quick sketch of what we've got going on. First thing I see is I've got -1 plus I. So -1 plus I, we're over here. This 128 will have to do with the magnitude of this complex number. So if I only had this yellow part, I would say my R value is equal to -1 squared plus 1 squared, or my R value is simply square root of 2. But this 128 extends that magnitude, so really my R is 128 root 2. Make sure you find theta using B over A. And the fifth root means your n is going to be 5. Make sure you check your answer in the back of the book. Come back when you're done. Are you going to try the wrap-ups for examples 8, 9, and 10 in your notes? Number 1, use de Moivre's theorem to find the quantity 1 plus I to the 6th. Make sure you have the formula handy. Number 2, find the fourth root of 1. So 1 is not in trig form, but you could rewrite it as 1 plus 0i. On the coordinate plane, it would be right here. So it looks like theta would be 0, and your R value is 1. Because you're finding the fourth roots, you'll be using k equals 0, 1, 2, and 3. And for number 3, find the 3 cube roots. So your n is 3. Your z is -6 plus 6i, so draw a very quick sketch of it. So -6 up 6, so it looks like you're working in the second quadrant. So make sure you find your theta using tangent of theta equals b over a. You're finding the 3 cube roots, so you'll be using k equals 0, 1, and 2. Come to class with questions tomorrow. I'll see you soon.